Alright students, let's debrief kinetics consolidation exercise 1. For the first question, you were told that you have two gases, NO and H2, reacting to give you N2O, and they react in a 2:1 ratio. Okay, and from a previous experiment, you were told that the order of reaction with respect to NO is found to be 2. Okay, so for this particular experiment, you are supposed to determine the order of reaction with respect to H2. Okay, and also something that you might want to take note of is that the initial partial pressure of NO and H2, they are found to be 200 kilopascal and 10 kilopascal respectively. This is quite important because if you write a rate law, or rather a rate equation, it will be written as rates is equals to K partial pressure of NO squared, because you were told that's second order from an early experiment, and then partial pressure of H2 to the power of M. Okay, and since you are told that NO's partial pressure was given to be 200 kilopascal, H2 10 kilopascal. So that means that the partial pressure of NO in this particular experiment is way greater than the partial pressure of H2. And this will make it a pseudo nth order reaction with respect to H2. Yeah, because if you rewrite the rate law, you write it as rates is equals to K prime partial pressure of H2 M. Okay, so that means that in the course of the reaction, you don't expect the amount of NO to change appreciably. Okay, so in this case, K prime is given to be K partial pressure of NO squared. Okay, yeah. So normally before you do a question, it will be good to go through some of these thought processes before you even jump into doing the question. Yeah, so that you are confident and you are sure about what you are doing is correct. So that's quite important. Something that I want you guys to take note of. Okay, and going straight into the question, you actually have the graph of partial pressure of N2O being plotted against time. Okay, so before we will move on, this is actually a product time graph. Okay, so you have partial pressure of N2O against time in the x-axis. So for the first part of the question, you are supposed to use the graph to deduce the order of reaction with respect to N2O. Okay, so maybe we can do a little bit of a revision on this. Okay, so normally we are familiar with what we call a reactants time graph. Okay, so for a reactant time graph, we have the concentration of the reactants being plotted against time. So in this case, let us assume that the reactant is A and my product is B in a 1:1 ratio. Okay, so if we take the initial concentration of the reactant to be A, and let's say this is an exponential decay, so we are going to find the half-life. For the first half-life, it will be A over 2, and the second half-life will be a quarter A. Okay, so from here we can determine the 2T half, and then we'll check out if they are constant. So if they are constant, we will deduce that okay, it need not be exactly constant, it could be relatively constant. Okay, maybe the difference is about 5%. I think that's fine. Okay, so if it's relatively constant, or even if it's constant at a fixed value, then you can deduce that this is actually a first order kinetics with respect to the reactants. Okay, so of course in most cases you can get a very beautiful graph like this, and then you can find consecutive half-life. Consecutive half-life means from A to A half, and then A half to A quarter. Okay, but you know that sometimes the question can be maybe a little tricky, so you can't really find consecutive T half. because maybe the graph only goes until, maybe I'll use a blue line, maybe the graph only goes until here. So it didn't reach, and or it purposely didn't want to draw until beyond maybe 60%. Yeah, so in this case, you can't take consecutive t-half. And please do not extrapolate. Okay, so do not extrapolate. Extrapolate is a huge mistake. So you shouldn't be extrapolating. Then what should you do? Okay, what you could do is you will just find non-consecutive t-half. So maybe I can check out a point here. Maybe this is 0.9a. Okay, then I will check out this point, and then I will check out another point, maybe somewhere here. So this point may be 0.45a. Okay, and then I will check out these two values. Okay, based on the time axis. Yeah, so I will check if this t-half, the one circled in red, is similar to the one I circled in orange. Okay, similar again, about 5% error lah. Okay, so if it's within that range, then yeah, you conclude that it's relatively constant. So in that case, you can conclude that it's first order kinetics. Yeah, so I think that works pretty fine for reactant time graph. Okay, the next thing to ask would be, what about product time graph? Okay, so for product time graph, as the name implies, we are plotting product concentration against time. Okay, and of course we start off from 0 because initially there's no product. So if it's a first order kinetics, of course you will get a graph that looks similar to such curve. Okay, but the thing about product time graph is it's a little bit more difficult to determine the half-life. Depends on what kind of product time graph you are given. Okay, so I'm sure you have met up with the current challenge in this particular question, because in this particular question you are given a product time graph and you guys might have difficulty determining the order of reaction respect to H2. Yeah, so in our case here, let us revise a little bit. How do we get the order of reaction respect to the reactant when we are given product time graph? Okay, so the principle that we should follow is actually similar to reactant time graph. Okay, in terms of picking the timing. So for example, for reactant, let's say going from A to B, right? If it begins with 100% A, okay, and we have 0% B, okay, so in our case here, that will be A and 0 here. Okay, so after the first half-life, I'm going to get 0.5A. Okay, that's the amount. And then for B's case, I will also get 0.5A. So why is that the case? Because they react, I mean A decompose in this case reacts in a 1. I mean 1 equivalent of A gives you 1 equivalent of B. So it's a 1:1 ratio. So if 0.5A amount of A reacted, I will get 0.5A of B. So I mean that makes sense. So in this case, we are looking at the first t-half. Okay, then if we can get consecutive half-life, so that's 0.25A, then in this case I'm going to get 0.75A here. So that will give me the second t-half. Yep, so in that case, for product time graph, the first t-half we should be getting is actually based on the total amounts of the potential total amount of product I can get from A. So in this case, if all the A reacted, then the amount of B I'll get is actually A. Yeah. So very importantly, you need to start from A. Okay, so in this case, I need to maybe replot the graph a little bit. Okay, so it will go something like this. Yeah. So A will be the maximum point that I'm looking at. So that's A. Okay, so I will just go down to this level. I'll look at 0.5A. Yeah, so this will be the first t-half. The next t-half is actually 0.75A, which is over here. Okay, so this will actually be the second t-half. So first t-half, second t-half. Yep, and then if I can find these two values, yep, then I will be able to obtain, I will be able to find out whether it is first order kinetics or it is non-first order kinetics. Okay, yeah, so using the same idea, right, let's take a look at the consolidation exercise. Okay, but of course, in this particular consolidation exercise, we met up with one major problem which you need to solve before you even try to determine the order of reaction respect to H2. Yeah, the first major problem is you need to determine the maximum amount of N2O that will be produced in the course of the reaction. Yeah, so it's important to determine that, because if you don't determine that, then you cannot solve the problem. Okay, so I think, well, I mean, it depends. If you're sharp enough, you realize that it's actually 10 kilopascal in terms of partial pressure. I mean, the reason being, if you take a look at, in this case, right, we started off with 200 kPa of NO and 10 kPa of H2. So therefore, the partial pressure of H2, which is related to the amount of H2 present, is actually synonymous, or is directly related to the amount of N2O that we produce. Yeah, because in this case, H2 is actually the limiting reagent. So in that case, I can conclude easily that the maximum partial pressure of N2O, or the maximum amount of N2O that can be produced, is actually governed by the amount of H2 that I started off with. So in this case, the maximum amount of N2O I can have in terms of partial pressure, it will be 10 kilopascal. So you need to recognize this important fact in the very beginning. Yeah, because if you don't recognize this, you actually can't do the question at all. You can't on the question. Yeah, because if you don't do that, right, you will not be able to realize that I need to base this particular ratio, right, on 10 kPa, rather than, in this case, some students might take it to be 6.1. So if you started with 6.1, then you are actually on the wrong track already. Yeah, so I need to start to determine the maximum amount of N2. So therefore, I need to begin by looking at the max, which is 10 kilopascal. Okay, so based on 10 kilopascal, right, I need to look at my first T half. So in this case, my first T half is actually from 0 to half of 10 kPa. So that will be 5 kPa. Okay, so this will be my first T half. Okay, which we can try to do that quite easily. Let's not do it now. Okay, we'll do that later. Then the next T half will be, if we are looking at consecutive T half, right, it will be from 5 kPa, okay, to 3/4 of 10. So that will be 7.5 kPa. Okay, so this will be the second T half, which is a consecutive T half. However, you notice that there is a problem that we will face, because we cannot extrapolate the graph. Yeah, very, very important. We cannot anyhow extrapolate the graph, and there's nothing to extrapolate to, even if you want to, because there's no more axis, there's no more graph, no more scale, so you can't anyhow extrapolate. So if you can't extrapolate, what can you do? Okay, so we are coming back to the same problem. Remember earlier on, I was showing you this particular blue line. Yeah, I will show you this particular blue line. Yeah, if you cannot, if you are just given the graph halfway, it did not even hit the 1/4 mark, what should you do? So you don't have to take consecutive half-life. You can take 0.95, 0.98, and then 0.45a. That can be done, right? So can we do the same thing for product time graph? Yeah, yes, we can actually do the same thing for product time graph, but it's not that straightforward. Yeah, it is not that straightforward. The reason why is it not that straightforward is I cannot anyhow choose a random point. So meaning I can't choose like let's say from 0.25 to 0.5. I can't do that. Yeah, because that doesn't work. Remember, that only works for reactant time graph, because the reason why I can't choose 0.25 and 0.5 is because if you correspond it to the amount of reactant, right, we are not really looking at half the amount of reactant reacted away. Yeah. So in that case, right, you must remember one important thing. The reference points must always be related to the reactant. Okay, so therefore we need to rework on this a little bit. Okay, so let's say we choose a convenient point. I mean, just for the purpose of illustration, I decide to choose, let's say, 0.8a lah. Okay, that's 80%. Okay, then in that case, my T half, which is half the amount of reactant, will be 0.4A. So I will choose this as my non-consecutive T half, and correspondingly, the amount of reactant here will be 0.2A to 0.6A. Now, do you notice this? Yeah, it's a bit different, right? It's quite different from what we originally imagined. Okay, so we're not going from 0.2 to 0.4. Instead, we're going from 0.2A to 0.6A, meaning 20% to 60%. The reason being, we have to correspond it to the reactant and not the product itself, because the product itself don't make sense. So with the same idea, we're going to do it for this. So yes, we have at least until 60%. Yeah. So in that case, can we do that as much as possible? So in this case, since I'm going to choose 80% of H2 to 40% of H2, right? Yeah. Then the amount, or I mean the partial pressure N2 I'm looking at will be from 2 to 6. So in this case, I'm looking at non-consecutive half-life. Yeah, and that's fine. That's fine. That's like perfectly fine. Okay, so shall we look at the graph and see if the T half is relatively constant? So in this case, I'm going to zoom in a little bit. I'm going to remove this as well. Okay, I'm going to zoom in a little bit to see. So zoom. Okay, so first maybe I'll look at from 0 to 5. Okay, so from 0 to 5, it's around here. Okay, so it's around, I mean, it's not so clear, it's around here. So so if it's around here, that's like 26,500. Would that be okay? Is it 26,500? Yeah. So this first point I'm getting is actually 26,505. Okay, so that's fine. Okay, how about we look at 6? So for 6 over here, it kind of like cuts relatively nicely around the halfway point. So in this case, we are looking at halfway point. So that's like 35,250, maybe 35,250 and 6. Okay, then we'll look at another point, which is at 2. So yeah, it kind of like cut quite okay-ish here. Like maybe I zoom in a little bit more. It cuts here. Okay, so that will be, let's see, that's 9,000, 8,005. So it's 8,750. 2. Okay, so in this case, can we do a quick calculation? So in this case, we'll get the T half. So we'll just do a quick calculation here. So T half from 0 to 5 kPa. So that's 26,500 seconds. Then T half from 2 to 6 kPa. So that would be 35,000. Oh, sorry. 35,250 minus 8750. So I'll use the calculator to do a quick calculation. So yeah, I'm getting about 26,500 as well. Okay, so that's excellent, because in this case, I'm actually getting constant half-life. So that's great. Okay, so from here you can conclude it's actually first order kinetics, because the half-life is constant at 26,500 seconds. Okay, so remember that when you write your conclusion, if you obtain a slightly different half-life, okay, you need to take the average and tell us that it's relatively constant at this particular average values, and then therefore you conclude that it's first order with respect to H2. Okay, so therefore first order with respect to H2. Okay, yep, would that be alright? So this is actually H2. Okay, in that case. Okay, yep. So we'll move on to the next part. Hence, write out the rate equation for the reaction. I don't think this is, of course, this is definitely not going to be challenging, because we have already written out a rate law here. But in our earlier rate law, we don't know m. So in this case, you can just put m as 1. Okay, so therefore, our rate law will be rate is equals to k partial pressure of N2O to the power of 2 and partial pressure of H2 1. Okay, right. Oh, sorry, not N2O. What am I talking about? It's actually NO. Yeah. Okay, so yeah. So just correct this. Apologies. Yes, it's NO. Yep. And in this case, calculate the rate constant K of the reaction, stating clearly its units. Okay. Yep. So I don't think this will come across as any big issue, but I mean should there be any issue, please let me know. I mean offline. Yeah. So in this case, the easiest way to do this is really since you have already determined the T half to be 26,500 seconds, right? Yeah, so from here you can easily obtain K because T half is ln 2 over K, so therefore K is equals to 1 over T half. Sorry, not 1, ln 2 over T half. Yeah, and then therefore I just need to punch my calculator, substitute my T half to be 26,500, and then in this case I'm going to get 2.616, okay, times 10 to the power of minus 5 per second. Okay, now however, right, at this stage, right, I want all of you to actually move back a little bit, because remember this, we are actually looking at this K. Okay, is this K the same as this K? So apparently it is not, right? They are not the same thing, because remember here we are looking at a pseudo first order reaction above. So above we are actually looking at a pseudo first order reaction. Okay, so in this case, right, we are actually not calculating K here. We are actually calculating K prime. So you have to be very, very sharp to recognize this. So here we're actually calculating K prime. We're not calculating K. Okay, so I need you to be fully aware. We are looking at K prime here. So this K prime equals to 2.616 times 10 to the power minus 5 per second. If you leave your answer as this, you will actually be marked down, because the question wants you to calculate K, not K prime. Okay, so earlier on, we have already defined what K prime is. It's K multiplied by partial pressure of NO squared. Okay, and partial pressure of NO is given to be 200 kilopascal. So in this case, my actual K should be 2.616, okay, divide by, sorry, times 10 to the power of minus 5, divide by 200 square. Okay, so I hope there's no major issue with this. Yeah, so remember that we were saying that K prime is equals to K partial pressure of NO squared. So in order to get K, we need to divide K prime by partial pressure of NO squared. Okay, so in this case, we are going to get 6.54 times 10 to the power minus 10. The units will be kilopascal minus 2, S minus 1. Okay, yeah, so it's a little bit complicated. That's the way kinetics goes. You really have to take note at what exactly you are calculating and what you are determining. Yeah, so kinetics is, as I've said all this while, it's not really a straightforward physical chem topic. Yeah, so there are certain things you need to be very familiar with. You need to be familiar with the definition. You need to be aware of what you are doing in every step, and seriously, memorizing will not get you too far. Okay, so it's of vital importance for you to understand the concept and apply them accordingly. Yeah, that will really help a lot in your journey in kinetics. Okay, so that's the advice I have for you. I think from day one, I've shared this with all of you at certain point in time. Okay, yep. Next we're looking at mechanism. So the proposed mechanism for the reaction is given to be as follows. So you have a fast equilibrium of two NO molecules colliding to give you N2O2, and then you have K2 here, the second rate constant, N2O2 reacting with H2 to give you N2O and H2O. Okay, and you were told that the actual rate equation was found to be this. Wow, such a complicated rate equation. Yeah, and you were told that given that the first step in the proposed mechanism is a fast equilibrium step. Okay, that's something you want to highlight. It's a fast equilibrium step, right? Show how the above rate equation could be simplified to the one which you have written in part B. Okay, so how are we going to simplify it? Okay, so first of all, you were told that your first step is a fast equilibrium step. Yeah, so in that case, you would expect, okay, because being fast equilibrium step, right, you would expect the values of these two, K1 and K minus 1, right, okay, to be way bigger than K2. Okay, why is that the case? Well, I mean, fast equilibrium step means that they kind of like dominate in terms of rate constant. I mean, the rates of reaction is very, very, very fast. Yeah, so therefore, I would expect the rate constant value to be way greater than that of K2 because K2, I mean, from the way or from the interpretation of the mechanism, from the question, from the information given, you know that it's likely to be a slow step here, and this is likely to be, then this is given to be a fast step. Yeah, so you can come up with this particular conclusion. Okay, and from the above, okay, I mean, there are several ways you can look at it, but in this case, to plan this particular experiment, you also plan it in such a way that the partial pressure of H2 is given, I mean, it is used at a very low values. Yeah, but that aside, right, because the question sort of limits me in so the question sort of forces me in that sense, forces me to get to the rate equation I've written for part B. Then what I should probably do here is, okay, so if this two value is way greater than K2, so can I then look at the denominator and conclude that therefore K minus 1, right, in that case, right, it could be way bigger than K2 pH2, partial pressure H2. Yeah, so if that's the case, then you realize you can actually sort of rearrange the expression a little bit, because when K minus 1 is much greater than K2H2, then you can say that therefore the denominator K2 plus K2 partial pressure H2, right, is approximately defined by K minus 1. Yeah, so therefore I can simplify the rate equation to be rate is equals to K1, K2 over K minus 1 partial pressure NO squared partial pressure H2. Yeah, and you notice that when I re-express this as the expression, this becomes the K over here. This becomes the K here. Okay, and the rest is the same. This P partial pressure NO squared partial pressure H to the power 1 is the same as this. Okay, yep. I know some of you might be wondering, how come we can make such an assumption that K minus 1 is way greater than K2 partial pressure H2, and then therefore this whole thing is approximately the same as K minus 1. You can just imagine that, let's say this value is, let's say 1000, and let's say this value is, let's say 10. Yeah, so can we approximate 1010 to 1000? I think we can do that, right? So if you think about it from that perspective, then you will be able to come up with this reasoning. But of course, some of you might be wondering, so to what extent do we do such approximation? If let's say K2H2 is 100, can we do such approximation? So obviously, if it's 100, in this case, the approximation will not be that accurate. Okay, so yes, that is a defining point, and that that boundary, okay, is really beyond the scope of the syllabus here. Yeah, so I guess in the future, if you take up a discipline in chemistry and then you delve more into kinetics and you'll be using computers to do approximation, then I think it's easier for you to come to terms with how can we better make use of such approximation to rewrite our rate law. Yeah, but in our case here, I think we are just looking at something from a very simplistic perspective. So from a very simplistic perspective, I think this is what we can come up with. Okay, yep. So again, let me reiterate that for H2 question, you work on it based on the context given to you. Okay, so when you work on it based on context given to you, I think it's easier for you to work through the problems and then get the answers appropriately. Okay, then finally we have you are asked to sketch an energy profile diagram for the reaction. So given that the reaction between NO and H2 is exothermic, by reference to the mechanism in the sketch an energy profile diagram, since you were told that the first step is a fast equilibrium step, so I expect the activation barrier to be really low. So in this case, maybe we have energy. So an energy profile diagram is energy plotted against reaction coordinates. Okay, and then so the energy profile diagram. Okay, so again, the first step, so we have two humps. So the first step is actually a fast equilibrium step. So therefore, the barrier is likely to be low. So we are probably looking at something like that, a low barrier. Okay, and then followed by the next step, which is having a high activation barrier. And then since you were told that it's exothermic, yeah, the product should be lower than the reactant. Okay, so in this case, if you draw a dotted line, so this is the reactant, so that's 2NO plus H2. So in this case, this is the delta H given to be exothermic. Okay, the first one is actually EA1. EA1. The next one is EA2. Okay, and we need to label the product as well. So the product here is N2O plus H2O. We should label the intermediate as well. So that's N2O2 plus H2. Okay, it will be good if you can label the transition state, although it's not necessary. So this is actually TS1, transition state 1. Okay, sorry, it should transition state represented with a double dagger, so that, and the other one is transition state 2. Okay, that should be it. As to whether you should be drawing out the transition state, my answer to you is no, not for H2, not a requirement for H2. So not to worry about that. Okay, yep. Then we'll move on to the next part, which is question 2. Okay, so for question 2, you were told that you have this compound known as butadiene, right? C4H6. It dimerizes via a Deuce order reaction to yield a substituted cyclohexene, C8H12. You don't really need to know what a Deuce order reaction is. If you're interested, you can go and find out. It's a Nobel-winning work. Okay, and then this particular gas phase reaction occurred at 400 Kelvin. Experimental data recorded in the table below. Okay, so you're given this particular table. You have the time. Okay, so from 0 to like 10,500 seconds, and then you have the total pressure in torr. Okay, and then so for part A, it's quite unusual in that sense because now they ask you to show something. Okay, so it's a bit different. So maybe it's something that you might want to take note of lah. Okay, so they ask you to show that at any time t, the pressure of C4H6 is given by the equation below, which is partial pressure of C4H6 equals to 2 times total pressure minus P naught. P naught is the initial pressure. Yeah, so you might be wondering, how can I possibly show this? Because it seems that uh, it's a bit seems complicated at the start lah. But actually no. So basically, the first thing you need to do is you need to just write a balance equation. So that will be C4H6, and because it dimerizes, two of it dimerizes to give you C8H12. Okay, then well, I mean, it's really flexible because it depends on how you want to go about doing it. Quite similar to what you expect in stoichiometry. If you recall in your lecture notes, you were given some techniques or some ways where you can attempt those gas calculation quite easily. So yeah, you can do that in a similar way. So in this case, the first thing I need to do is maybe I want to write down an pressure, initial partial pressure. Okay, of course it's in torrs lah. Okay, TORR. And then since the question already gave me a P naught here, okay, a P naught. So I might as well just leverage on it lah. So I can just call this P naught. Okay, and this of course 0. Okay, because initially I do not have any C8H12. Okay, then what about at any time t? You know, like any time t, what would the change be? So maybe I can put change at time t. So change at time t, right? If let's say I'm forming X amount of this, so let's say I'm forming X amount of this, then the amount that changes for C4H6 will be minus 2x. Okay, then therefore I can easily calculate, or I can easily write down an expression for the partial pressure at time t in terms of torque. Yeah, so that will be the difference between these two. So that will be P naught minus 2x, and in this case will be x. Okay, then can I then perform a calculation to determine the total pressure at time t? Isn't the total pressure at time t the summation of P naught minus 2x and x? Yep, so this will give me, oops, sorry. So this will actually give me the total pressure at time t. So that's P total, P total, okay, equals to P naught minus x. Okay, then I need to express it in terms of x. So this will be, so x is actually equals to P naught minus P total. Okay, right? However, I need to go back to the question. The question is asking me, show that at any time t, the pressure of C4H6 is given by this particular expression. So in this case, I need to express it in terms of P naught minus 2x, right? So therefore, the partial pressure of C4H6, okay, is actually P naught minus 2x, right? Okay, then I need to substitute x equals to P naught minus P total into here. Okay, so I think that becomes very clear now. So in this case, I'm going to end up with P naught, okay, minus 2P naught, okay, plus 2P total. Okay, so and this is equals to 2P total minus P naught. Yeah. So you just need to perform a little bit of algebra and you'll get this. Okay, and of course, you'll be wondering, why are we getting this? Okay, you need this later on. So you gotta chill a little bit and I think slowly work through the problems and you'll know why you need this. Because this is important for you to solve the whole of question 2. Okay, and then for part B is a bit of mathematics here. So if you saw how I worked through the integration to prove to you first order kinetics, you can actually use the same method to work through this, okay, at your own leisure. So anyway, I just show you a little bit as well. I mean, I just show you how to do it, and I guess it will also help you to maybe learn ordinary differential equation earlier on, before you learn it in H2 mathematics. Okay, so it's the same thing. So I have minus dA dt equals to k a squared. Okay, so again, I'm going to rearrange them a little bit. So I'm going to rearrange them to get 1 over a squared dA equals to minus k dt. Okay, so same thing, exactly the same thought process. I'm going to perform an integration. Okay, I'm going to perform an integration. The limit is from time 0 to time t. Okay, and in our case here, it will be from a0 to a. So after performing the integration, you will end up with minus 1 over a naught. Sorry, not 1 over a, minus 1 over a. And from a naught to a, and this is equals to minus kt. Yep, and then so you're gonna end up with minus 1 over a plus 1 over a naught equals to minus kt. Okay, if you multiply minus 1 on both sides and then you shift 1 over a naught over, you're going to end up with 1 over a is equals to 1 over a naught plus kt. Okay, so that's how you prove this by integration. Okay, yep. And then of course, part C, they ask you to hence or otherwise show that the dimerization of C4H6 occurs via second order kinetics and obtain a value for the rate constant. Okay, since they ask you to show that it occurs via second order kinetics, we have to be a bit strategic in the way or in the kind of graph that we aim to plot. Okay, that's very important. Okay, so in this case, I mean, for me, usually usually to simplify matters, and of course, given the nature of the question, I will need to look back above, okay, and see whether I can plot something. I can plot something from here. Okay, so of course I can easily plot something from here because I think first of all we will try to plot a straight line because at the end of the day I need to obtain a value for the rate constant. Okay, and we saw that there's a kt here, so if we plot something against maybe t and then find a gradient, if it's a straight line then the gradient will just give us k. Yeah, so we have to be a bit strategic in what we are plotting. Yeah, so I think in this case the simplest line to plot we can actually plot will be 1 over a minus 1 over a naught equals to kt. Okay, so we can simply plot this against t, and if it's indeed a second order kinetics, we will get a straight line that passes through the origin. Okay, so in our case here, it will not be a or a naught, it will be 1 over in this case our a is actually the partial pressure of C4H6 lah. So let's do that. Okay, yeah. Of course, there are many ways to do it. If you want, you can choose to plot 1 over a against t. That's fine also. And then you get 1 over a naught as the y-intercept. That's fine. Okay, so it's very flexible. Okay, so we'll try to plot, and then the graph paper is given here. So of course, I'm not going to plot it using the graph paper here. Okay, I mean, if I want to, I can, but yeah. So I'm just going to do it in a quick way. I'm just going to do it using Excel. Okay, and we'll see whether we can get any results out. Okay, so yeah. So the first thing I'm going to do is I'm going to copy the values over onto the Excel sheet. Okay, over here. Yep. So I think first of all we are given time. We are given the total pressure. Okay, so just going to do it in a relatively quick way. So the time we're given is 0, 750, 1500, and then after that I'm just going to drag it down to 10,500. Okay, the total pressure we are given, it's actually let's see, 626,579. Okay, so I'm just going to copy this over. 626, 579, 545, 510, 485, 465, 450, 440, 425. Oops, I think might have made some mistake here. Let's see. Okay, I think the values aren't that straightforward. It's 1005, and then 2460, 3425, 4280, 5140, 6000, and then 7,500, 9,000, and then yeah, so so too much values earlier. Okay, yep, and then so that's the P total. So remember that this is actually okay. So earlier on, right? Just go back to just go back to earlier on. You are asked to express the partial pressure of C4H6 in terms of P total and P naught, and then you get this expression. So you're supposed to prove this. So you realize that even if I cannot prove this, I can still carry on and do this particular question. Do you recognize that? Yeah, so this is a way to ensure that the students will not get penalized for not being able to do the mathematics in part A. Okay, so yeah, so let's do that. So we just do P total minus P naught. So we can do that. So that's P C4H6. Okay, yeah. So that's equals to 2 P total, okay, minus P naught, which is the initial one. Okay, and this value is kept a constant. Okay, so I'm going to change it to the dollar sign. Okay, yeah. Okay, and then I'm going to drag it down to get the rest of the values. Okay, beautiful. And then the next thing I'm going to do is I'm going to calculate the reciprocal of the partial pressure of C4H6. You'll be wondering why I do that. Because of this. So, because remember, I'm supposed to plot the reciprocal minus of 1 over P naught against time. Okay, so I'm going to do that. So, I'm just going to paste this over. Okay, like this. Okay, so the reciprocal will simply be this is equals to 1 divide this. Okay, let's keep the values to 3SF, or rather yeah, 3SF. Okay, so I'm going to drag it down. Okay, so in your case you have to punch the calculator. Okay, so yeah, so it's actually easy to do via Excel. Yeah, so this is this. The next one will be minus 1 over 626. Oops. Okay, sorry, not in this case P naught. Okay, yep. So this will be equals to this minus this. Okay, so I'm going to do the same thing, put a dollar sign to keep it a constant. Okay, and drag it down. Just make sure that they are 3SF, 2SF. Yep. Okay, and then I'm going to plot excuse me, this against T. Okay, so I'm going to insert a graph, scatter plots. Okay, to see if it's really a straight line. Let's check out the values to see that nothing's amiss. Okay, right, so just going to remove the title. and then I'm going to add a trend line. It's a linear line. Okay, so that, yeah, that takes. Yep, almost done. It's okay, so you're going to get a relatively nice graph here. So I'm just going to zoom into the graph. Okay, and find the gradients. Okay, so in order to find the gradients, we might need to make our line as thin as possible. Okay, yeah, so that we can cut through the appropriate points. Okay, so in this case, I'm just going to zoom into this particular point. Yeah, maybe over here. Just going to take, yeah, over here. So that's 0.00400 on the y-axis, and then zoom. And on the x-axis, it's around so every unit is 1,000. No, it's 100. Okay, so let's go zoom a bit more. That's 10,000 450, or 10,450. Yes, 10,450. Yep. Okay, so we go back to this. So my gradient, okay, will be change in y. So the change in y here is 0.00400, 0.00400 minus 0, divide by 10,450 minus 0. Okay, so just punch in the calculator, and I will get about 3.82 1 2 3 4 5 6 7 times 10 to the power of minus 7. Okay, as the gradients. Okay, and of course the y-intercept is 0. Okay, and then what about the units? So remember that we are plotting the reciprocal of partial pressure against time. So therefore the units will therefore be tau minus 1, and then per second, or rather seconds. Yep. Sorry, divide by time, so that's per second. Yeah, okay, can. Yep. So I think that's the end of the debrief. I hope you find it useful. So do expect consolidation exercise 2 to come up next.